Hello, everyone. Finally, it's the last presentation. I know it's not easy for everybody to stay here for all day. Thanks for coming. I'm Wang Geng from Asian Info. Asian Info is a software vendor in the field of telecommunications in China. A couple of years ago, the telecom carriers in China, such as China Mobile and China Telecom, began applying big data technologies in their operational, supporting, and networking system. For example, the carriers built up their new data warehouse based on Hive in their operational analysis system and charging list query system based on HBase. Today, I'd like to share our practice on streaming data processing in telecom. Based on the requirement of our customer, we have designed and developed a streaming processing system. We call it OCSP, which has been used in many scenarios of the telecom and has good usability and performance. Okay, let's start the presentation. This is the outline of my presentation, and it has 4 parts. First, I will give an introduction on the streaming processing scenarios which we faced in the telecom carrier today in China. And then I will share the framework of OCSP and some detailed technologies. After that, we will see how OCSP meets the performance requirements such as high availability, scalability, and high performance. In the end, I will share the work we are going to do in the future to enhance this system. And if we still have time, I will give us a demo view to see how OCSP works. Okay, let's turn to the scenario first. Nowadays, mobile telecommunication means more than voice service. We all know that. Data service plays a main role in our daily life, especially after the wireless networking upgrade to 4G. The data produced by the networking sharply increased in every single second. This is a big challenge and a great opportunity for telecom carrier. From one side, new business would be generated based on more detailed information. On the other side, it's more difficult for engineers to develop to process the huge amount of data, especially in some real-time data processing. Okay, this slide shows 2 typical scenarios which originated from real-time data in telecom. First is smart tourism. As we all know, when the mobile is powered on, it communicates with base station time to time, no matter whether there is a phone call. In the view of telecom carrier, the location info contained in the signals can be used to locate every single end user. With this info, some statistical work can be done. For example, if the real-time location, your name and gender of each subscriber is available, you can count the total number of all the tourists in some specified area. Furthermore, we can get the real-time heat map. Based on the real-time heat map, the administration department can launch early warning if the number of tourists explodes and and can recommend other routes for tourists if needed. Another scenario is intelligent marketing. In case of this tourist business, CEP system is a shortcut for complex event process. CEP system like Esper is a classic tool which can work everything out perfectly. But as upgrading of the wireless tech, huge amount of streaming data would flood to CEP. and it didn't work anymore. So something new should be involved to the system to fix these issues up. This timeline shows the evolution of our system. Before 2014, CP system was used in real-time marketing. In 2015, streaming system based on sparse streaming has been used to process the signal data of 2G and 3G. The scale of data is about 2 million records per minute. In 2016, more data are included in the system. 4G signal and content data was directed to the streaming system. The scale of data came up to 22 TB per day. This is all real-time data. This year, in 2017, some strict real-time requirements such as anti-fraud detecting tosses to us. The system must finish processing the data within 1 second. So this is a big challenge for us. Let's turn to the framework of OSSP. Before this slide, I want to know how many of you have used the sparse streaming, red sparse streaming application? How many of you? Oh, okay. We all know that it's not easy for developers to write sparse streaming applications. So from the high level, OSSP abstracts the streaming process to 3 stages. First, data input. In this stage, streaming data flows into the stream. In addition, input data is pre-processed in this stage, such as filtering the invalid record, formatting according to schemas. The second stage is tagging, which is the most important stage. In this stage, labels with key value pairs describing the meaning of the data are attached to the original record. Actually, the main business logic of streaming processing is implemented in tagging stage. It seems like you call it a user-defined function. We call it tagging in this system. I will explain it later by examples. Output stage filters the data after tagging based on the configured rules. This step made the decision whether to output the data and how it is outputted. Okay, this is the architecture of OSSP. It consists of 3 layers, including basic components layer, OSSP core layer, as well as data transformation layer. Basic component layer includes some components in Hadoop and Spark. We use HDP as software stacks. OSSP is built on top of them. Next is OSSP core layer. According to the sequence of processes, OSSP consumes data from Kafka and then processes the data by sparse streaming engine or Storm engine. Finally, the results are written to Kafka again. In the tagging stage, streaming engine gets labels from Redis, which is an in-memory cache, and attaches the label to the original import data after computation. Data transformation layer is a pipeline. It gets data from outer system, parses the original data to text messages, and writes the message into Kafka. We use Flume or NiFi to do this work by customizing a Flume source and sink or NiFi processors if needed. There are 3 advantages of OSSP. First, there's no need to implement a sparse streaming or Storm applications from end to end. OSSP provides interface for tagging. With these APIs, developer can customize the logic function in the streaming. Second, OSSP has an outstanding performance in production. Since we did some performance optimizations, it has been proved in different kinds of scenarios. Thirdly, OCSP had a good usability. It provides UI to create, configure, and monitor the streaming process. And also it supports multi-tenancy for streams. This slide describes data transformation. OCSP gets different kinds of data from outer system. If using Flume to transform data in the Flume sink, the data will be written to the different partitions based on a partition rule. The number of partitions, we all know that if you use Spark streaming, we all know that the number of partitions in Kafka is mapping to the number of parallel tasks in Spark streaming. So the partition rule should avoid the data skew for more higher performance. When original data comes into Kafka, streaming engine consumes it and formats the data in every macro batch with specified schema. In this process, the RDD data are transformed to data frame first. Then SQL such as select and filter can be applied to the data frame. Within this step, invalid data and unused fields will be discarded. Okay. Now I will explain what is labels. As I said, tagging is the most important step in OCSP. Labels will be attached to the original data after tagging. Labels are some key value pairs. This page shows some sample of label. For example, user info label here describes the basic user's information such as name, gender, and age. This is some key value pairs. The key is the name. The word is the name. The value is the user's name. This information is pre-stored in Redis. When streaming engine gets a value from Redis, it will be attached to the original data. This step is called tagging. After tagging, we have got enough information. It's flexible for OCSP to decide whether outputting a message and which fields will be selected. This rule can be configured in SQL language. Currently, OCSP also supports writing the result to multiple topics, Kafka topics based on different output rules. So it's dark. Each process in OCSP is configurable. And OCSP also provides web and RESTful API to help user configure the process. Okay, let's see the performance of OCSP. With the benefit of open source projects such as Spark and Yarn, each component in OCSP can be scaled out. In the stage of data input, Flume can be scaled out by adding agent. In the streaming processing step, OCSP uses Yarn as a resource scheduler of Spark. We all know that Yarn has a good usability and performance, also has a good scalability. Let's get back, revisit the smart tourism case. See how does OCSP made it. In this case, the data source is 4G signal from the core network. The information elements in the signal not only include the EMC, location, timestamp, but also contains some unused fields. EMC is an identifier binding a signal record to a subscriber's user. With the combination of these three values, a user can be located by location code, but the processing is not over because Even the original location info can be passed from the signals. The information is not understandable by human. Then we need to map IMSI to the detailed information of a user and the location code to the longitude and latitude of the base station. These information maps are called label. To achieve the goal of getting the heat map, OCSP needs to attach the labels to the original record. First, the data comes from a core network are written to Kafka view flow. And then OCSP fetches data and filters the invalid records. For example, if we get data without IMSI or location, it's an invalid data and will be discarded. And then in the tagging stage, OCSP queries the labels which is cached in Redis or Redis, and attaches the labels to the signal record. After that, the data are written to Kafka. In this case, the latest user's information, longitude, and latitude we got under stable information. And we can do some statistical work to generate the real-time heat map. This page is the time cost I collected from 2 of our use cases. In case 1, in 30 seconds, which is an interval of Spark streaming, each macro batch can be processed in 5 seconds. In case 2, each macro batch can be processed in 17 seconds. About 10 million records will be processed. These 2 cases shows that OCSP has a good performance, since we handles about 22 TB data per day for case 2. Okay, and last, here is some work we are going to do. First, we need to support more scenarios. For example, we need to handle some cases for the join of multiple streams in a time window. And we need to support more streaming framework like Storm, Flink, and so on. The next is we need to be faster. To achieve this goal, we need to do some keep the pace of Spark upgrade, such as structured streaming, and we need to use some faster cache. And last, we need to get the high availability of OCSP, since we need to have no single point in the whole framework. The last, we contribute our code to GitHub, and you can find OCSP code and some document from this address. Okay, I'll give you to see. Right? From this website, you can get the OCSP code if you are interested. And the document, some of them is written in Chinese, but we have translated most of them to English, so you can get them. And the introduction and also some framework, and you can download the package we have built, or you can download the check out the code and build it yourself. Okay, we still have some time, and I'd like to share you a video demo. This is something like a streams analytics, which is described in today's keynote for HDF 3.0, but it is streaming analytics is built on Storm. We use OSIP is built on sparse streaming. So when you log in the system, you can create a sparse streaming using a simple wizard. You click the name and select the Kafka topic for data input. And after that, you can input the schema of the data source. After that, we also support read data from different topics of Kafka. So in the wizard, you can input multiple topics. And after that, you can select labels, which is pre-built in the system. And each of them is a user-defined function. After that, you just need to select which topic you want to output the streaming and how to put it based on the filter condition and select fields, which field you want to output it. After that, you just need to submit this job, and from the UI, you can configure it, and after start it, you will launch a sparse streaming backend. Okay, we also support some dashboard you can get the more information of the streaming, which is running backend, such as you can get the elements, the streamings for each user created, and the time cost for each streaming. So that is a summary of the streaming processing. Okay, it's similar. Okay, please.
Question.
Yeah. Okay. That's all. Thank you. Yeah. Okay.
For smart streaming, like I believe the driver might be single point of failure.
Yeah, we use. Okay, please.
How do you plan to address that part? Like, is that something you're changing in Spark, or do you have some alternate solution?
No, we don't have changed any feature of Spark. We just use it. So we use Yarn to start it, and if the driver failed, Yarn maybe can launch it. Okay. And sometimes we use a streaming cluster within a Hadoop cluster. We use Yarn to label the host to which is running the streaming, and Yarn will put all the streaming tasks to these selected hosts to run streaming jobs. And for other batch jobs, Yarn will launch the jobs to other hosts. We use this Yarn feature. Okay, please.
So I saw Storm in your architecture. Why did you have Storm there?
Okay.
On the pictures. Was he using for something?
Not this demo.
Not the demo.
Right.
The presentation. Yeah.
Which slide?
The architecture slide.
It's a diagram that talked about your architecture.
The framework, right?
Yeah, that.
It is?
Yeah. In the middle section it says Spark and Storm both.
Yeah. First we use sparse streaming as a streaming engine.
Okay.
Yeah. And right now, our team is working on Storm engine. So when user use OCSP, he did not see the detail of the backend, and he can change the different engines. But for Storm engine, we are working on it, not released yet. Yeah.
So in the Spark streaming, what was your data volume? Like, the data frequency, how much was it? Is it 1 second data, like 100 hertz data? What is how much when it says streaming?
Yeah.
Real-time streaming and still is micro batching?
Yeah, macro batching. Yeah. So since we need to handle huge number of data in telecom, so the most number of the batch of record is about 100 million records per minute or per 30 seconds.
Per second.
So yeah, we need to have more throughput.
Records per second.
Yeah. 100 million to 150 million records per minute. Yeah. It's all about signals from our phone to base station, so it's a big number. Right, thank you.
How did you fix the out of order messages? Number one. Number two is, what are the query patterns on HBase?
Yeah, I will answer your number 2 question since I understand your number 2 question first. We use HBase, right? You mean why we use HBase and what way to use it? Yeah. For the smart tourism case, we need to store all the current location for each end user. So we need to store it in HBase. But you know Kafka is a message queue from real time, so we use Flume between Kafka and HBase. So when the real-time data, which contain the recent location for each user, comes after processing by Spark streaming, and it will output to Kafka, And since that, we will use in Flume to update HBase. It's a table to update HBase from the Kafka message. Understand? That's why we use HBase. We use it to count the number of the current location for each user. So we need to get a snapshot of the current location for every user. It's about one of our cases is about 60 million user. Yeah. Really? I can.
Out of sequence of the messages, how did you handle it?
How many sequence?
Out of sequence.
Out of sequence.
Yeah.
OCIP supports multiple streams and sequence. And when you log into the system with we support LDAP login. So when you log into the system with LDAP user, each of you have the authentication by LDAP, right? And when you create a stream, the backend Spark streaming on Yarn will be launched by the login user. You log in, right? And since Yarn supports multi-tenancy on different queues, yeah. So we support multiple streamings based on Spark streaming and Yarn, right? So we support multiple streamings in the same time, yeah, based on the Yarn scheduler, right? Right? Any other questions? Okay, thank you for again.